So let's talk about the ratio test. The ratio test, much like the alternating series test, the geometric series test, and the p-series test, is going to be one of those tests that you're going to use quite a bit compared to, say, the integral test or the direct comparison test. So the ratio test allows you to look at a series and to compare the n plus first term to the term before the nth term, and to judge by that ratio whether or not the series converges. So this is kind of like the direct or limit comparison test, but we don't need another series to compare it to. We can actually compare it to its individual terms. So I'll let you write this test down. Go ahead and copy it down into your notes, and we're going to talk about how this works. So before we do any examples, so you understand that we're doing a limit of the n plus first term to the nth term. So statement 1 basically says if that limit goes to something that's smaller than 1, meaning it's shrinking appropriately, then that means that this series is going to converge, that the terms are going to shrink at a level where eventually the sum will approach a single number. The series diverges if that ratio is bigger than 1, because if that ratio is bigger than 1, that means that the terms as you move towards the end are actually getting bigger by net. So that means that there's no way that that sum can converge. And the big thing is that the series is inconclusive if L equals 1, because that means they're kind of, once you get out towards the end, they're sort of growing at the same rate, so it's hard to tell if it's actually converging or diverging. Now, I've got a couple of examples that are just straight up ratio test, and then the ratio test is super useful because this is what we're going to use with power series and with Maclaurin series and with Taylor series to talk about their convergence. So first, a couple of examples. So the first one we're going to do is this series 3 to the n over 5 to the n plus 1. Now, anytime you see exponentials, numbers to a variable, or you see factorials in a series, it's almost always going to involve the ratio test. So those are some cues you can look for when you're trying to figure out if you use the ratio test or not. So when we go to use the ratio test, we're going to take the limit as n goes to infinity of the n plus first term, which literally means take the basic term and plug in n plus 1 for all the n's, divided by the nth term, which is literally the term that appears next to the sigma. Now, with a ratio test, you're always going to have a fraction stacked on top of a fraction, so it's same switch flip. And now we're going to look to simplify this fraction. So if you look at the three things, you have 3 to the n plus 1 on top, 3 to the n on bottom. So when you divide things that have the same base, you subtract the exponents. So that would be 3 to the n plus 1 minus n, which is 3. And we can't do a similar simplification on the 5s because there's that plus 1 there, but we're going to deal with that in the next step. So when I come down here to take my limit, I have this, and then I have this. Now, when I take my limit, highest degree terms will matter, right? Because we're doing basically an end behavior here. So the highest degree term I have on top would be that 5 to the n inside the parentheses, and that 3 on the outside is still going to be sitting there. And then on bottom, the highest degree term is that 5n plus 1. It's going to outstrip whatever the plus 1 does by quite a bit. So now that I've gotten that down, now I can simplify those 5s, and again, I can use my rules of subtraction for exponents, but this time I'll end up with a 5 on the bottom. So the limit as n goes to infinity of 3/5 is 3/5. That's less than 1, therefore, this series converges. So let's look at this red problem over here. Again, we have exponentials and factorials appearing, so we're going to go ahead and do the ratio test. N plus first term divided by the nth term. I'm going to do a same switch flip, but I'm going to do some simplification here too. So let's see, I've got 2 to the n plus 1 on top. 3 times n plus 1 is 3n plus 3. And then that factorial is going to turn to n plus 2 factorial. And then when I do the flip of the bottom fraction, that will give me 3n n plus 1 factorial over 2 to the n. So we talked about how to simplify the exponentials. We can do a subtraction of the powers. So this would end up with a 2 on top. Oops. Didn't mean to do that. Let's just erase that. N goes to infinity. There will be a 2 on top. Now, the factorials, and we talked about this briefly in class, just want to reemphasize it. N plus 2 factorial would be n plus 2 times n plus 1 times n times blah, 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 blah. N plus 1 factorial would be n plus 1 times n minus 1, blah, 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 blah. So if you're looking at those factorials, all of the n plus 1 factorial is contained in the n plus 2 factorial, but then there's just an extra n plus 2 sitting out in front of all that. So that's going to simplify down to n plus 2. And then I have a 3n on top and a 3n plus 3 on bottom, which can't yet simplify. Now, going to take this limit, and again, it's an end behavior, so I want to look at the highest degree terms. On top, my highest degree term is going to be 6n. On bottom, if I were to FOIL that thing out, which I'm not going to do because all I need is the highest degree term, I'd end up with a 3n squared. 6n over 3n squared simplifies down to 2 over n, and as n goes to infinity, that goes to 0. That's less than 1, therefore this series converges. Now, we're going to do one more problem, but this one's a little more complicated. This one's actually checking for the convergence of a power series. Now, because power series have x's in them, it kind of depends on what x is as to whether this thing converges or diverges. So let me show you how that's going to look different than what we just did in the previous two examples. So again, I see an exponential, I see a factorial, I'm going to do the ratio test. By the way, the ratio test is pretty much what we always use for power series. So n plus first term divided by the nth term same switch flip. All of this is the same as what we did in the previous example so far. Now we're going to simplify the fraction. And this also simplifies. So what I end up with is this. Now, what you do at this point is you look at this stuff because n is going to infinity. You can ignore the x minus 3 for right now and basically say whatever involves n is what's going to affect the value of that limit. So if I put a 1 in front of all that, really what I'm looking at is what happens to 1 over 2 times n plus 2 as n goes to infinity. Well, if that happens, that limit is going to go to 0. So that's going to give me 0 times x minus 3 as the value of that limit. Now, sometimes that'll go to a number, sometimes that'll go to an infinity, sometimes that'll go to a 0. In this case, it went to a 0. So 0 times x minus 3 is always 0, which is less than 1. So in this case, it does not matter what value of x I choose, because the limit as n goes to infinity goes to 0. The whole thing is going to go to 0, and it's going to be less than 1. So this converges for all x. Now, when we come back together next time, we're going to talk about some problems where it doesn't converge for all x, and then we'll see how that looks.